All right, so today we're going to get started with some probability. And most of the data that we're going to use, if not all of it, is going to be within R. We're going to generate our own data and run our own experiments. The primary application of this type of approach is when you are trying to model some sort of phenomenon. So we're going to get started with a really simple examples, but you can imagine how these examples extrapolate out to then model and run simulations on millions of different variables. It's beyond the scope of this class, but this is a good introduction to how probability works and how when someone says that they ran models, this is what they're doing. So for the first thing that we're going to do is go over here, click on one of this white sheet with the green plus sign, and we're going to get a new R script. You can get it from File, anywhere that you get your new R script. And we'll go here, and we are going to pretend that we are flipping a coin. Now, the real reason that we talk about flipping coins is because we're looking for a true or a successful or a desired or a target outcome of two possible outcomes. A lot of times we can think of this as being like success or failure, true or false, whatever our target outcome is. For us, our target outcome throughout the rest of this session is going to be heads. We are looking for a heads. That means success. That means that we got the desired outcome in our experiment. Okay. For a typical coin, it is what we call fair. So there's a 50% chance of heads and a 50% chance of tails. All right, so let's get started with our coin. So if I want to just flip one coin one time and see what my outcome is, I can type R binom, and then I'll pass it one coin that I flipped one time, and it has a 50-50 chance, 0.5 chance. Go ahead and run that line of code, and this coin came up tails. Let's run it again. Gotta highlight it now. Run it again. That coin came up heads. So we could keep doing this all day, but we would probably get really bored. So let's go for a more efficient way of doing this. Instead of flipping one coin, let's flip 10 coins. So we just type R binom. We give it 10 coins. Each one of those 10 coins is flipped one time, and 0.5. So let's see what happened with all 10 of our coins. How did they each turn out? All right, and what we get down here is that the first one was tails, the second, third, fourth, and fifth were all heads in a row. Then we had a tails, then we had 4 more heads. So you might be saying, but wait, there's a 50% chance. Why is R doing this? Why is it taking these 10 coins and I don't have 5 heads and 5 tails? I have an uneven distribution. What's going on behind the scenes is that R is using a pseudo-random program to generate different outcomes. Okay? So it's just saying, you know, just like in the world, what comes up heads, what comes up tails. Okay, so now let's just to illustrate that, let's run it again. And here we also have two instances of tails. This is not proving my point terribly well. We'll run it again. There we go. Now we have a more even distribution, something more like what we would expect to happen. But all of these would be completely realistic. You can definitely imagine flipping a coin and it coming up heads, you know, 6 times in a row here, getting a couple of tails and then getting more heads. You know, after a while you might get scared, but you could imagine this happening. This is completely realistic. The next thing that we're going to do is then take just one coin, binom, and we'll flip that one coin 10 times. And what this is going to show us is how many times did it turn up heads. So rather than having our 10 coins each flipped one time, and it gave us how many times each individual coin came up heads, this is going to return to us how many times out of 10 our individual coin came up heads. Let's go ahead and run that. And here we get 6. So it looks not completely like any of these examples, but it would be as if we got 6 ones. So here we flipped our one coin 10 times and we got 6. We got heads 6 times. Let's look at one more. Now let's take 10 coins, flip them 10 times, and again, it's a fair coin, even distribution. Run that, and the first coin came up heads 4 times. The second coin came up heads 6 times, and so on and so forth. So now we're starting to look at our probability distribution. So what were the outcomes across all of these different trials? What does that distribution look like? All right, but you might be saying, not all coins are fair. There's quite a few trick coins out there in the world. And R has a way of handling that as well. So if we type R binom, and we have our 10 coins, and we flip them 10 times, but this time they're trick coins, and they are unfairly weighted for heads. So they disproportionately give a positive outcome or a successful outcome. So we go ahead and run this, and we see down here that it came up heads 9 times, 6 times, 7 times. Our numbers there are quite a bit higher. So now if we run another simulation with a coin that is weighted unfairly against a positive outcome, so its chance of coming up heads is less than 0.5, as we have here, our binom of 10 coins, flip 10 times, and we're going to set this proportion to 0.2, like we know the probability. Let's see what we get. And here we get numbers that are quite a bit lower than we were getting up here. We get numbers that we would expect from a coin that is unfairly weighted against a positive outcome. All right, so what we're looking at overall here is a binomial distribution. So any experiment that has 2 possible outcomes, either heads or tails, success or failure, true or false, anything that has a binary 2 outcomes can be modeled by the binomial distribution. All right, so now I'm going to start simulating many different outcomes. So rather than just running these lines one by one, I'm going to start assigning them to variables. So I have flips, and I'm going to assign it to the variable, or assign it to the function R binom, and I'll pass 100,000 coins. Now we're starting to talk about what might be in a sample or what might be in a population. Maybe there's 100,000 participants or 100,000 people. We'll pass it 10 events. Let's say each person does whatever experiment they're working in 10 times. And there's a 50-50 chance of coming out positive. So it is unweighted. And then we'll go over here and we want to see what the outcome is. So we're going to type hist and then flips, and we'll say probability equals true. And this should give us a graph of a histogram of the outcome of our flips here, which is just our binomial run 100,000 times. All right, so we'll highlight both of these. Go ahead and run it, and we have our histogram of our flips. So it's very nicely distributed here. We have a nice normal looking curve. And what this is showing us is how many times our flips came up 5, how many times it came up 4, 6, 7, 8, 9, and 10, right? So this is just our 100,000 coins graphed out here, just like we would have had in a row over here. If we had passed our binom 100,000, we'd have 100,000 different events. It's pretty impossible to understand that with our eyes, but once we turn it into a graph, we can start to understand what the distribution actually looks like. So now that we've simulated our many outcomes, we want to try to figure out what is the probability of having exactly 5 heads in one of these trials, in one of these events. So I want to know what's the probability of having 5 heads and 5 tails out of my 10 flips. And it might not quite what you expect. So we've already defined our flips up here. And I'm going to say when is flips equal to 5? And I'm going to go ahead and run this, and it's going to give me a whole lot of values. And what this is saying is that on the first time it was false, 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 true. So the first time that I got 5 heads and 5 tails was the 4th event. Okay, and then I have 3 more falses, 1 more true, more falses, a couple more trues. Okay, so I've figured out how many times that can happen, but that is also completely unintelligible to my human eyes. So I'm going to find the mean of flips is equal to 5. And we worked a little bit with means last week, and this is going to give me what percentage, what average of these is actually 5. What it's calculating is false is a 0 and 1 is a true, or true is a 1. So this is going to come up as a percentage. Let's go ahead and run that, and I get 0.247. So less than 25% of the time are you going to get 5 heads and 5 tails when you flip a fair coin. But that was rather cumbersome to figure out. First we had to run our simulation, and then we had to find the mean of our simulation. And R is far more helpful than that. So R has a way to calculate the exact probability density, and it's called D-binom. You may have guessed by now that all of these that are binomes are really they only apply when there's 2 outcomes, when there's your positive and your negative outcomes. All right, so the way that we calculate this is we say how many times we have a positive outcome. So for us, we pass it, we want to know when heads comes up 5 times. So this 5 represents our flips up here. And there's 10 flipping events, and it's a fair coin. So if we go ahead and run this, we get something slightly lower than what we got the first time. So what's going on here, And what's happening is that the first time that we ran this, we were running this on 100,000 coins. Here, we're actually calculating it based on a near infinite number of coins. If you've taken a calculus class along the way, this probably makes sense. This, a very large number versus approximating infinity or approaching infinity. If you haven't taken a calculus class, it's really not important. What this number represents is the theoretical probability density of getting 5 heads on any given set of 10 trials for a fair coin. Okay. As this one I find to be kind of fun to play around with sometimes. So if you do D-binom, let's say that we want to know what's the chance of getting 10 heads on 10 flips and a fair coin, right? So what's the chance of getting 10 heads out of 10 flips? And it is a really, really small percent. It's less than 0.1%, right? So let's then, the intro to Rosencrantz and Guildenstern, they've flipped a coin 157 times, and it's come up heads every time. So let's calculate what I like to call the Rosencrantz and Guildenstern probability. So we'll type D-binom. We'll pass it 157 flips. 157 of those come up heads. It's a fair coin. and we will run it, and it is really, really, really small. That e to the negative 48 means that you should move the decimal place 48 spots to the left. So there would be 48 zeros after that decimal before getting to the 5. So no wonder they get scared at the beginning of that play. All right, so all joking aside, the other thing that we often want to calculate is the cumulative density. Okay, so what is the chance of getting either a 0, a 1, a 2, a 3, or a 4? So something less than 5, right? So we don't want 5 or above, but we want to know what's the chance of an outcome being unfavorable less than half of the time, right? So if we go back to our original flips, which we still are holding onto our variable up here, and then if we type in the mean of our flips less than or equal to 4, so how many times do you get 4, 3, 2, or 1, or 0, right? So we'll go ahead and run this, and this is our simulated value. It looks like 0.378 is our simulated value of running 100,000 events, and then 10 flippings, and 4 of them or fewer coming up heads. Okay, so this is our cumulative density of flipping our coin and getting an unfavorable outcome less than half of the time. As you might expect, R has a very useful way to calculate this as well, and it's P binom. So we'll go ahead and type P binom here, and we will pass it a 4. So we want to know 4 favorable outcomes out of 10 flips and a fair coin. So we can go ahead and run that. And what we come up with is our calculated probability of getting 4 or fewer heads out of our 100,000 flips. All right. So the last thing that we want to look at in this section is what is our expected value? So if we have our 100,000 coins that are flipped 10 times each, what's the average of those flips? And as you might expect, it is just the mean of flips. And again, the reason that this works is because true is valued as a 1 and false is valued as a 0. So we'll go ahead and run that. And the mean of our flips is just slightly under 5, which is really close to what we would expect, right? Like we would expect the mean of our flips to be 5. And the theoretical mean of our flips is definitely 5. It's just a matter of, in this set of 100,000 experiments, it came out to slightly less than 5. So again, that's the difference between running these simulations and actually calculating what the number is going to be. All right, so we are going to move on and talk a little bit about the variance. So our expected value is this 5. It's the highest point here. But what is our variance? What is the span of the data? I'm going to look here at variance rather than standard deviation, but you can easily calculate the standard deviation by taking the square root of the variance. And the variance, as you might remember from last week, is the average squared distance between the number and one random draw. So we'll go up here and we will ask for the variance of our experiment. So what was the range, or what amount of variation do we see? So we'll go ahead and type VAR, and we'll pass it flips, which was our flipping experiment. Go ahead and run that line. And the variance of our flips, it's still calculating, is 2.489, or just about 2.5. which is exactly what we would expect given our given the fact that our mean was slightly below what we would expect as well. If you are more interested in working with standard deviation, you can also just pass SD and flips, and it will calculate it just as easily. And it's the square root 1.58 of our variance. All right, so that covers most of what we want to talk about in terms of binomial distributions of one event. We're going to turn our attention now to binomial distributions of two events. So if we have A and B, or A or B. First, we're going to start with A and B. So we're looking at the probability of two events happening. So we're going to set A, we're going to run an experiment with A. We're going to assign it to our binom, where we have, again, 100,000 flips. Just have one event here and a fair coin. We'll do the same with B. We will assign it to an experiment of our binom with 100,000 coins that are each flipped one time and that are fair. They have an equal probability. Okay, so if we run these two lines of code, we will run our two experiments. Go ahead and run that there. And then we can ask for the mean of A and, with the ampersand, B. So R gives us a little bit of a shortcut here and allows us to use the ampersand to calculate this. And this is the same formula, behind the scenes, this is the same formula that we looked at in class of, probability of A times the probability of B. So we'll go ahead and run that. And we have about 0.249 or 0.250, which is about what we would have expected, given that it should have been 0.5 times 0.5, which would be 0.25. But here, these did not come out, because they're experiments, because they're simulations, they don't come out to exactly 0.5. They're approximations of a 0.5. Okay, so let's look now at unfair variables instead. So let's set C, and we will assign C to our binom, and we'll do 100,000 coins, each flipped one time, but this time they're unfair. They're unfairly weighted in favor of heads. And for D, we will do the same. We'll do our binom and 100,000 coins, and they are unfairly weighted, but this time let's say they're in favor of tails. Let's make it a little bit different. So we'll have a 0.8 in favor of heads and 0.2 in favor of tails. We'll go ahead here and calculate the mean of C and D and see what we get. So we'll run these three lines of code, and we get far less of getting a heads and a tails. We can mess around with this to get it to about 0.25, but the point is that this is a really quick way to run a simulation to try to figure out a variety of different outcomes of a variety of different events. And as you might expect, we can also find the mean or the probability of A and B and C. And if we run this, we see what's the probability of getting a heads the first time, heads the second time, and heads the third time, noting that the third time we have an unfairly weighted coin. So go ahead and run that. And it comes out a little bit higher than we might have expected if they had all been fair, right? So we have about 0.1 1998 here, or about 0.2 is our average. Had all 3 coins been fair, we would have expected it to be right around 0.125, because it would have been A times B times C. Okay, so that's A and B. A or B is a little bit more complicated. So we'll use our same A or B, but as you remember from our lecture, A or B is a slightly more complicated function, but again, R makes this super simple. So we can type the mean of A. We use a pipe for OR. That's probably in the upper right-hand corner of your keyboard, possibly right above the Enters button on the right-hand side, Enter or Return. So we'll do the mean of A or B, run that line, and we see A or B is 0.75, just as we would have expected had we calculated this by hand. Just like with the ands, we can also calculate a whole string of ors. So we can look at the mean of A happening, or B happening, or C happening. And we would expect that this is going to be really, really high. Go ahead and run it, and as we see, it is really high, due in part to the fact that this is a heavily weighted coin, and in part to the fact that we just need one of these events to be true in order to satisfy the needs of our experiment. Okay. You can also combine ands and ors into the same sentence. So you can have the mean of A or B and C. Go ahead and run that. And what that means is that you have the A or B and C. And it's much lower than B or C, but much higher here than A and B and C. So you can go ahead and play around with that. When people say that they run simulations of different events happening, oftentimes what's going on is is a whole series of these events stacked together. And this is where domain expertise in order to create these scenarios really comes into play. You know, this type of calculation is often used in understanding risk around diseases spreading, or the possibility of stock markets falling or rising, or things like that. All of this is a really great way to run a whole bunch of experiments all at once and, you know, see what those outcomes are and try to calculate what risks we should take. And that brings us to the next really big thing that we're going to do, which is update from evidence that we have using Bayesian statistics. And Bayesian statistics is probably one of the most important things that we work in. And really, Bayesian statistics just means updating from probabilities that are known and calculating probabilities that are unknown. So we're going to get started here. And I'm just going to go down a couple of lines, give myself some new space. I'm going to say that I have a fair coin, and I'm going to assign the variable fair to an experiment, the R binom, of 100,000 outcomes, of 20 coin flippings of a fair coin. Okay? And I'm going to have my F is going to, I'm going to assign F to the sum of fair equal to 14. So I want to know how many times 14 came up out of our 20 flippings of this fair coin. Okay, so this is just the number of times that 14 turns up in this experiment. Now I'm going to do the same for a biased coin. All right. So I'm going to go down here. I'm going to say my biased is and assign that variable to another experiment of our binom, 100,000 events with 20 flippings each of a unfair coin. So I'll say this one's 0.75, okay? And I'm going to set B and assign B to the sum of biased equal to 14. So how many times did my biased coin turn up heads 14 times out of 20? Okay, and I'll run these 2 lines of code. All right, and I didn't ask it to print anything, so the only reason that I know that it ran is that it appears down in the console here. And I'm going to set my total equal to F plus B. Okay, so this is how many times my fair coin came up heads 14 times and how many times my biased coin came up heads 14 times. Okay. Run that code, store it in memory. Okay. Now, I want to know that the probability that the coin is biased given the fact that we got 14 heads. Okay. So even though we passed this biased weight here, we're actually not sure that our coin is biased. The reason being that first off, we have 100,000 coins, and second off, what we've passed here is not necessarily the bias of the coin, but the bias of the experiment. So if we turn up heads 75% of the time, which is what this is saying, is the coin biased? How sure can we be that we have a tricksy coin on our hands? Okay. So the way that we calculate this is that we're going to take B, the number of times that it turned up heads 14 times, and we're going to divide it by the total, which is the number of times that it turned up heads 14 times for both our fair coin and for our biased coin. Okay. And we will go ahead and run that, and what we get is an 82% chance that our coin is biased. Now this is a lot higher than the 0.75 that we have here. And what's going on is that this represents how sure we can be that this coin is biased. It's actually not that confident, even though, 3 out of 4 times it's going to turn up heads. We still can only be 82% sure. That means that we are 18% unsure. And as we know from our presidential elections, that's actually enough for it to turn out the other way. This could be a fair coin. All right, but as we know, that's an experiment. It's not an exact calculation. So we want to figure out an exact calculation. So the way that we're going to do this is with d-binom. So I'm going to set this to probability of fair. I'm going to assign that variable to d-binom. And I had 14 positive outcomes out of 20 flips of a fair coin, right? And the probability of biased, I'll assign that to d-binom of 14 positive outcomes out of 20 flips for an unfair coin, right? So what is the probability that our coin is fair as opposed to biased? So I'll go ahead and run that code, highlight both lines, run it. All right, and store those variables in memory. And now we can go ahead and calculate the probability that this coin is biased, the actual probability as opposed to the experimental probability. So we will, the same way we did before, the probability that the coin is biased divided by the probability that it's fair plus the probability that it's biased. And here we've used parentheses to make sure that this fair plus biased is calculated before the division here. Let's go ahead and run that. And we have 0.820, which is slightly less than our probability here, but there are some cases where that could make a difference, such as financial forecasting or various types of disease detection and things like this. So these probabilities actually matter, the difference between our experimental probability and our actual outcome. We're going to really quickly turn our attention to a couple other distributions. These are more just for fun than anything else. Next week, we're going to look in depth at the normal distribution, so we're not going to look at that right now. But another one that you should just be aware of is something called the Poisson distribution. The Poisson distribution is the probability of an extremely rare event happening. So to understand what this looks like, we would do our binomial. Again, 100,000 events, 1,000 trials, and 1 out of those 1,000 trials is actually a positive event. So if we go ahead and run that, what we come up with is our giant matrix. But as you might expect, R has a much more direct way of calculating the Poisson distribution, and it's R Pois, R-P-O-I-S. And we're going to pass it our population, and in this case our population is 100,000 individuals, and then the mean of our sample and the probability. So our sample was 1,000 individuals, and our probability was that 1 over 1,000 people, or 1 over 1,000 coin flips, would turn up positive. Really common for things like rare diseases or rare cancers is where you really often find the Poisson distribution. So visualizing this distribution is a little bit more complicated than other ones. So we're going to pass this line in. This line is hist, H-I-S-T, and then we'll pass in replicate. Replicate means do the same thing this many times. So replicate this distribution or replicate this function. That we're going to replicate 1,000 times the mean of the R Poisson distribution on our population of 100,000, and our lambda or our mean is equal to 1. And then there are 4 closing parentheses here. So go ahead and run that. And it'll take a second to load, but what you already see here is a non-normal distribution. This one's a little bit closer to normal, but again, it's not quite as evenly distributed as the other ones are. With slightly more fitting, you see that the Poisson distribution will often shift very far to the left as you get more rare of events. Okay, so the last distribution that we're going to look at is the geometric distribution. And this is kind of my favorite distribution because it's, in my mind, I often call it the subway platform distribution because it's about waiting for an event. So if you are going to model what your time on the subway platform looks like and how long the average person needs to wait before the next train comes, you'd probably want to use a geometric distribution. So the geometric distribution is best modeled by waiting for heads. So you keep flipping your coin, and however many times you flip it, you only care about when you get heads. So we're going to manipulate this function just a little bit. So we're going to set it equal to a variable. And I'll call it flips1 because I've already used flips. And I will assign it to our binomial, and there's 100 coins that are each flipped 1 time, or 100 different subway platforms with 1 person on them, and the probability of this turning up heads is 0.1, or a 10% probability. So we'll go ahead and run that. And then we've stored our flips variable. And then we want to ask which one of our flips turned up heads first. So we will type which flips 1 equals 1. And then we'll run that. And the first, the 29th, and the 68th events were all heads. The first event was heads. Okay. So the next thing that we want to ask was, when was the very first time that that heads was the first variable? So what was the first time that we had to wait for it? So what was, when did our subway car come? So we type which flips 1 equals to 1, and we want to get the first instance of that. So unlike some other programming languages, you call the first instance with the number 1 as opposed to the number 0. Go ahead and run that. And the first time that our coin toss or came up heads was actually the very first time. So we wouldn't have had to wait very long. As you might expect, R has a shorthand for this. So R has the geometric distribution, or RGeom. So I'm going to type RGeom. I'm going to pass it 100,000 instances. So I want to see, if there's 100,000 people on subway platforms. And again, my probability is 0.1 here. So I'll go ahead here and make a histogram to illustrate my results. I'll type hist and then pass it replicate 100 times the mean from the R geometric function with 100,000 instances and a probability of 0.1 and 4 closing parentheses. So go ahead and run that. And you should see a histogram come up. We will look a little bit more at this if this is relevant to your project this semester. Until then, don't worry about it too much. But you can go ahead and export these plots, and you only have to upload one to the LMS, and that will complete your tutorial for tonight. Please let me know if you have any questions, and I look forward to working more with probability with you. All right, have a good night. Bye.